All right, welcome everyone. Welcome back. Homework 4 is due a week from tomorrow. So based on what we're doing in class today, I recommend trying problems 3.70 and 5-26 after class today. And just as a reminder, these three problems on homework 4 are material on the binomial distribution that we covered last Friday. Because we're skipping this Friday as far as when homework is due, homework 4 is a bit longer than the past few homeworks have been. So I would recommend trying these 5 problems after class today or this weekend rather than waiting until next week and then trying to do all the homework before it's due next week. All right. Let's talk about the binomial distribution a little bit. So at the end of class last Friday, we went through a proof that if y has the distribution binomial with parameters n trials and probability of success p on any one trial, then the expected value of y equals n times p. And that was a pretty long, complicated proof. So I wanted to summarize it to sort of go over the key points, because these are ideas that will come up again and again when you're trying to prove things about the expected value or variance of lots of different distributions, not just the binomial. So what we wanted to prove in that proof was that the expected value of y for a binomial distribution had a particular formula. So in this case, n times p. The way we started with that was with the definition of expected value that says the expected value of y equals the sum of y times the probability of y over all the values of y for that random variable. We made that specific to a binomial distribution by replacing p with the formula for binomial probabilities. And while we were at it, we also changed this all y to be as y goes from 0 to n, because those are the valid values of y for a binomial distribution. We did algebra to simplify that formula then. And then we noticed that the part inside the summation looked kind of like a probability from a binomial distribution. We noticed that it looked like a constant times p raised to a power times q raised to a power. And we did algebra to make it look more like that. So that was the substitution of variables we did with z equal to y minus 1 and m equal to n minus 1. And the whole point of that was to try to get it into this format where we could use the fact that if we take the sum of probabilities over all possible values of a random variable, that sum equals 1. So that let us simplify our formula a whole lot and get rid of the whole part with the sigma, so that we were just left with n times p times 1. So this part, these last 3 steps, that's a common trick that you'll use in probability to prove things about expected value and variance, is noticing that the part inside the sum looks like some kind of probability, and then doing algebra, rearranging it in order to make it fully be a probability, so then you can use this fact that probabilities add up to 1. questions about this? All right. One other formula for a binomial distribution that you're going to want to know is the variance of a binomial distribution. So this equals n times p times 1 minus p, or n times p times q. And this is proved by a similar method to how we proved the expected value of a binomial distribution. And if you want to read that proof, it's on page 107 of Wackerly. All right. So now let's switch over here. So recall, we talked about the binomial distribution. Can someone remind us when the binomial distribution makes sense to use? What sort of situation does it model? Sam?
I've written when the outcomes are binary.
The outcomes are binary, yep, so it's like flipping a coin. But what else? What else is important about that? Kyle?
A random process.
A random process, can you make that more specific?
Like a random outcome.
Yeah, Vivian?
Independent.
Yeah, we need it to be a random process where the trials are independent. Sam, did you have the same thing? Cool. So we have multiple trials that are independent. Each trial has the same probability of a success or a yes result, and that's P. And a crucial thing with the binomial distribution is that the random variable y that we're interested in is the number of successes or yes outcomes in a fixed number of trials, where n is the number of trials or repetitions or individuals that we're sampling. And in that case, here was our formula for the probability that y equaled y. So we said that this was take the probability of a success times itself for the number of successes that you want, because the trials are independent, so we can just multiply their probabilities to get the probability of their intersection, times the probability of a no result, so Q is 1 minus P, raised to the power of the number of no results we want. And then we multiply that by the number of ways that we could order n trials with y successes. So that's to account for the fact that all we care about in this probability is getting y yeses. We don't care about the order in which those yeses occur. All right, we just talked about that. So now let's compare that to a geometric distribution. The geometric distribution is good for modeling independent trials where the probability of success on any one trial is P. This bit is exactly the same as the binomial distribution. So the thing that's different about the geometric distribution is what our random variable y represents. In a geometric distribution, y represents the number of quote-unquote failures, or no results, before the first yes, or the first success. So both of these, geometric and binomial, we can think about as flipping coins. But in the binomial distribution, you plan ahead, I'm going to flip 10 coins, and I'm interested in the probability of getting y heads. A geometric distribution, you don't plan how many times that you're going to flip the coins. You just say, I'm going to flip coins until I get my first heads. And I want to know the probability that I need to flip the coin y times before that first heads. So for the probability that our random variable capital Y equals some specific value little y, we have the formula q to the y times p, where q is 1 minus p. So this is the case because in order for the first success to be on the y, or on the, in order for there to be y trials before the first success, we need to have a success on trial y plus 1. And before that, we need to have y no results in a row. So q to the y times p. And here we don't have that n choose y business in front, because with the geometric distribution, the order matters. We need to have our trials be in the order y copies of a no result, and then a yes result. Questions about this? What values of y is this formula valid for? If you're flipping a coin until you get heads, what are the possible numbers of times you might have to flip tails before you get your first heads?
You should do it forever.
Yeah, so there's no upper limit. Is there a lower limit?
You could do it on the first try.
Yeah, so if you got heads on your first try, then y, your number of tails, would be 0. So this formula is valid for integers, y equal to 0, 1, 2, ... with no upper bound. So, for example, in Wisconsin, 61% of people who take the bar exam pass it and become lawyers. If different attempts are independent, what's the probability that Gary, that's my dad's name, he's a lawyer, will pass on his third try?
0.09.
0.09. Does that agree with what other people got? So here, why the number of no results before the first yes is 2, because if he's gonna pass on his third try, he needs to have not passed on his first 2 tries. So we have q to the y is 0.39 to the 2 times p, which is 0.61. Oops. So I actually didn't write down what that is. Is that 0.09? 0.092781. Cool.
That's what I got as well.
Excellent. What's the probability that he'll need more than 3 tries, which you actually need to partition the bar association to get permission to take it more than 3 times?
One minus 2.2.
What's that?
1 minus 2.2.
How'd you get that?
Complementing.
What's that?
I just take the probability of pass on third try. 1 minus that.
So you're on the right track. You do want to use the complement rule here, but the complement of more than 3 is 3 or fewer tries.
Oh, okay. .96.
0.96. So we're looking for the probability that y is greater than or equal to 3. So we can write that as 1 minus the probability that y is less than or equal to 2, using the complement rule. And we can find the probability that y is less than or equal to 2 by taking the sum of the probability that y equals 2. So that's the 0.39 squared times 0.61 that we found up above, plus the probability that y equals 1, plus the probability that y equals 0, which would be passing it on the first try. Oh, I didn't write down what that answer is either. Pooja says 0.1521. Does that agree with what other people got? Sam, you getting a different number?
Yeah. Well, when I put that in, I get 0.05.
Yep, see.
0.05.
0.05931.
0.059, what?
9319.
9319. Pooja, that's what folks in the classroom here are getting.
That's what I also got on my first attempt of that.
Okay, sounds good. All right. So here's a question. We justified this q to the y times p formula using ideas of treating the trials as being independent and caring about the order. But does that justification make it a valid probability distribution? What do we need for this to be a valid probability distribution? 2 things. Values between 0 and 1, and and the probabilities add up to 1. So let's check those. So first is the probability of y between 0 and 1 for all values of y. Well, p is between 0 and 1 because it's a probability of a yes result on any one trial. So q is 2 because q is 1 minus p. So if p is between 0 and 1, then q is also between 0 and 1. So when we multiply a bunch of copies of things together, and all of the things that we're multiplying are between 0 and 1, their product is going to be between 0 and 1 as well. So that part checks out. So how about the other criterion? Is the sum of the p of y's equal to 1? Let's try to prove this. So first of all, the sort of generic thing that we're interested in is the sum of p of y over all y. But this is a geometric distribution, so we can make that more specific and say we're specifically talking about the formula p of y is q to the y times p. And our sum for all the valid values of y is really a sum over the integers from 0 to infinity. P doesn't depend on y, so we can factor it out. So we can say that this is p times the sum of q to the y, as y goes from 0 to infinity. So now, let's call this summation of q to the y. Let's call that s for sum, so we can work with it separately. So we have s is the sum of q to the y. Let's write that out, expanding the sigma notation. So when y is 0, we have q to the 0, so that's 1. When y is 1, we have q to the 1. Then when y is 2, q squared plus dot, dot, dot. Any ideas about what our next step should be? To try to figure out what s equals. This is a trick that we've seen once before in this class. Let's multiply s by something convenient. So let's try q times s. So every term in s gets multiplied by q. Why is that a convenient thing to multiply by?
Because then you can substitute qs into the equation, the first equation.
I think there's something we want to do first. Let's subtract these two lines. So let's take s minus qs. So every term that's in qs also appears in s. So the q's are going to cancel, q squareds are going to cancel, q to the thirds are going to cancel. When we do the subtraction, the only thing that we're left with is this 1 at the start. So s minus qs equals 1. So then we can factor out an s. So we have s times the quantity 1 minus q equals 1. And then divide both sides by 1 minus q. And we've figured out that s equals 1 minus q. But q was 1 minus p. So 1 minus q is p. All right, so we figured out that s equals 1 over p. Now let's take that back to the sum we were originally interested in, which was the sum of p of y over all the values of y, which was p times s. Bum, 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 bum. That's now p times 1 minus p. So we've proved that that equals 1. So we've proved that even though this is an infinite summation, it really does add up to 1. So the geometric distribution is a valid probability distribution. Questions about this? All right. Why were we doing this? Oh yeah, because this proves that q to the y times p for y being integers from 0 without bound is a valid probability distribution. Okay, some important facts about the geometric distribution. The expected value of y is q over p. And the variance of y is q over p squared. Kyle.
So just to reinforce this, Q is the probability of failure and P is the probability of success.
Correct.
Okay.
Q is the probability of failure, P is the probability of success. All right, we talked last time about how to work with a binomial distribution in R. To work with a geometric distribution in R, it's going to follow the same structure. So we have the same 4 prefixes, D, P, Q, and R, depending on what we want to do. And then we attach those onto the stem geom for geometric. So for example, D geom 3,4, the prefix D gives us the probability that y equals exactly some value y. So this is going to give us the probability that y equals 3 when we have a success probability on any one trial of 0.4. P-geom, 3,4, the prefix P gives the probability of y being less than or equal to some value little y. So that gives us the probability that y is less than or equal to 3 when our probability of a yes on any one trial is 0.4.
Generate random numbers, how does that one work?
So that would be our geom. Say we want 1,000 random numbers, and success probability on any one trial 0.4. Does that answer your question?
So it just generates a random number that could be decimal point anything.
So it'll generate random numbers that are valid values of y from this distribution. So for a geometric distribution, the results you're going to get are going to be non-negative integers. So with a value of 0.4, it's going to be sort of more tending towards low numbers, 0, 1, 2. But if you're generating 1,000 of them, you probably will have some that are larger, 10, 15. Oops. All right. Something to be aware of with the geometric distribution is that there's also an alternative parameterization where your random variable x represents the number of attempts required to get the first yes result, including the yes. So here, our formula for the probability that x equals some specific value little x is q to the x minus 1 times p. And this is valid for values of x equal to 1, 2, 3, 4, ... with no upper bound. But here, 0 is no longer a valid outcome because we're counting the yes result. So at a minimum, we need one trial to get the first heads, for example. So this alternative parameterization is the version that Wackerly uses. Hassett and R use the first version that we saw that's letting the random variable be the number of failures or no results. Let's let y be the number of failures before the first success, and let x be the total number of attempts until the first success. Try finding the expected value of x. And you can use what you know about the expected value of y. So if you've written x in terms of y, and you're thinking about using theorem 3.5, you're on the right track. So the number of attempts until the first success is one more than the number of failures until the first success, because it's just all the failures plus the one at the end that was the success. So how can we rewrite this expected value? Yeah, the expected value of y plus the expected value of 1 by theorem 3.5. And then by theorem 3.3, the expected value of 1 is a constant, so the expected value is just 1. Then we can plug in q over p. We know that's the expected value of y. So the expected value of x, getting a common denominator, is q plus p over p. And we can simplify that using the fact that q equals 1 minus p. So that is 1 over p is our expected value of the total number of attempts until the first yes. The variance of x is still q over p squared. So the same as the variance for the number of failures. Can someone give me an explanation of why that makes sense? What was the thing that you proved on the last out-of-book problem on homework 3? Anybody remember? It was one of our important facts about variance. That was the variance of y plus a constant equals the variance of y. So here we're doing exactly that. We're looking for the variance of y plus 1, and that's equal to the variance of y. All right. So overall, these two different parameterizations, one of them is based on the number of no results until the first yes, and one of them is based on the total number of attempts until the first yes. It doesn't matter which of them you use, as long as within a given problem, you're consistent. So that means that if you choose, oh, I'm going to let x be the total number of attempts until the first success, and then you go into Hassett and you look up, wait, what was the formula for the expected value of a geometric distribution? You need to be aware that of which version Hassett is using. So pay attention to the difference between Hassett and Wackerly and R in this, and just bear that in mind when you're using those as references for the expected value and for the probability distribution.
Would you mention like which one to use or we have to analyze also?
For any given problem, you can pick. So it'll make a difference as far as like whether you're finding the probability that y equals 1 or the probability that x equals 2, but it's the same probability, just calculated in slightly different ways. Because it's a matter of whether you would have like q to the 2 minus 1 times p versus just q to the 1 times p for the probability. Like fundamentally, those are the same. All right, did I share my screen? I don't think I did. Okay, so let's try applying these ideas. A telemarketer has a 5% chance of making a sale on any given phone call. What's the probability that their first sale occurs on the 10th call? Vivian, got an answer?
0.03151247.
0.035?
0.0315.
0.0315? Does that agree with what other people got? Cool. So 0.95 to the 9 times 0.05? Excellent. How about their expected number of calls until a sale? I totally forget whether I meant including the sale or before the sale. I said until, so probably including the sale. Yeah, so 1 over 0.05 is 20 versus the expected number of non-sale calls until a sale, so before the sale. Kyle?
Would it just be 19?
Yeah, and you can get that in either of two ways. What's one of the ways?
Just the 20 minus 1?
Yep, so we already found that the expected number of calls until a sale, including a sale, was 20, so you could take that minus 1. The other way would be to use the other formula for expected value. So Q divided by P is 0.95 divided by 0.05, and that gets you the same answer. All right, and finally, what's the variance on the number of calls they need to make until they make a sale. Kyle?
Is it 380?
Yeah, we have 0.95 divided by 0.05 squared, so it's 380. That is a pretty big variance. It's often easier to think about this in terms of the standard deviation. So the square root of 380 is a little bit less than 20. And it makes sense that we would have a large standard deviation here, because with a 5% chance of making a sale at any given call, like sometimes they're going to be successful on their very first call. But sometimes, like some days, it might take them more than 20 calls. It might take them 40 calls. So when we average those out across many different days, we have a lot of variability from the expected number, 20 or 19, depending on what we're measuring. We have a lot of horizontal variability around that central value for what could occur. So we end up with a large variance for the geometric distribution. All right. Thank you all for your attention. I will see you tomorrow for the negative binomial and hypergeometric distributions. Any questions from folks online? All right.